Lily and Nolan, did you just log on or had you been logged on with me not here?
You've been here for a couple minutes.
Oh, I think
Yeah.
I first opened the wrong meeting this morning.
Oh, yeah, must have been last quarter's.
Because I've got several of them on my Zoom account. Oh well, I got to the right one eventually. Let's see, I have opened the first module. I don't know if you saw it. I've got the Word documents you can access for the problems we're going to do today and some additional ones too. And then also in that first module, well, it's not the first one on the list, but it's the one for the first unit we're studying. I put the first homework assignment up last night as well. So that's up there. And it's getting close to start time. I also got yesterday's video posted, and yesterday I went out to school and recorded a video of me with this piece of rotational inertia equipment and a couple of different distributions on there. It's a little blurry. The classroom computers I don't have access to installing software on, so I couldn't install my webcam software on it, so it didn't focus, but it's still usable anyway. Okay, well, let's get going on stuff. Today I want to start with solving some problems, but actually before I do that, I want to show you something here. Let's see. This is the first page of the day one thing for rotations, the Word document that I put out. And it has some real simple questions, just considering a wheel of radius r rolling without slipping along a horizontal surface for a total of 10 rotations. And they should be relatively simple things. This is an exercise that we can usually do in the classroom, and it doesn't take too many minutes to get this done. But it's looking at some things related to just rotational motion for a wheel rolling along on a road. And it turns out that when you calculate the angular velocity of the wheel, the linear motion of the wheel, the speed of it is equal to the radius of the wheel times omega, even though that omega is viewed from the center of the wheel, thinking of it that way. And there's just some interesting things. And in the next chapter, we'll look at some rolling motion thing and readdress this issue. But you might try just working through these problems to convince yourself of a few things. Now I'm going to jump on to this thing and solve some problems. And when I do these problems, I'm going to kind of model, at least on the first one, I'll model the way that I want you to write homework solutions this quarter. They're not going to be as detailed as they were last quarter. And in fact, you may find it just as fast to do them by hand, especially if you're not familiar with the equation editor. But here we have an electric motor rotating a workshop grinding wheel at a rate of 1.00 times 10 squared revolutions per minute is switched off, and assume constant negative acceleration of magnitude 2.00 radians per second squared. We've already got a mixture of units here because the acceleration is radians per second squared. I guess you could express an acceleration in revolutions per minute squared, but we're not going to do that. Anyway, and you've got a rotation rate, which is an angular velocity in revolutions per minute. But we want to know how long will it take to stop and through how many radians will it turn during that time. So for every problem you do, I want you to start with a given and to be determined. And so given here, we have a wheel with an initial rate of 1.00, or an initial angular velocity, we could call it. And you might see this written as just 100, but when it's written in scientific notation like this, you can clearly express the correct number of significant figures. So just writing it as 100, you don't know that. We've got 3 sig figs. Anyway, is switched off. And slows to a stop with an angular acceleration of 2.00 radians per second squared. Okay, so that's the crucial information. It doesn't matter that it's an electric motor, that it's a workshop grinding wheel or anything else. The crucial information is it's a wheel with an initial angular velocity of that. It's switched off and slows with a constant. I should have said that with a constant angular acceleration of 2 radians per second squared. And then B, or the to be determined part, would be for A, how long will it take to stop? And B, through how many radians does it turn during this time? So this may take almost longer to write than the solution here in this case, but and I can fill this out into a more thorough sentence. Through how many radians does the wheel turn while stopping? Okay, I'm not usually going to do this on problems, but it just shows you the way you should start your things. And hopefully you have neater handwriting than I do. Since I don't write as much by hand anymore, my handwriting has gotten worse as I've gotten older. I do better typing. Anyway, let's figure this out. And we can use some of the relations that we developed yesterday. But the first thing we need to do is to fix that angular velocity. We have that omega is equal to 1.00 times 10 squared revolutions per minute, that's not going to do it for us. We've got to convert that into radians per second. And so we'll just multiply by our funny looking ones, 2 pi radians per revolution. Okay, and then another funny looking one is, let's see, 1 minute over 60 seconds, and that'll get us to where we need to be. Okay, it'll take care of the revolutions. We'll have radians per second when we do that. And whoops, always helps to turn the calculator on first. Okay, actually I get, let's see, 10.5 radians per second. All right, well, we've got constant negative angular acceleration, and so I can say that alpha is equal to negative 2.00 radians per second squared. And if I want to know how long it takes to stop, the easy way is to use our constant angular acceleration formula. That's sort of like our v equals v naught plus at equation, except for us, it's going to be omega equals omega naught plus alpha t. And actually this is omega naught up here. That's the initial angular velocity. So I want to know when omega is equal to 0. So I'll just have 0 is going to equal 10.5 radians per second plus alpha t, whoops, alpha. I have a number for that. Hopefully you do it neater than I do. Minus 2.00 radians per second squared times t. Now, when you solve something like this, this is elementary algebra. You can just go ahead and write t is going to equal 10.5 radians per second divided by 2.00 radians per second squared. You don't have to explain these algebra steps or anything like that. In fact, you don't have to explain the algebra this time unless you do something really fancy. But that'll just equal heck, could have done this in our heads. 5.25 seconds. Okay, so there we have that solution. And this is adequate for solving a problem. I started off with the equation in variable form. Actually, I started off with defining terms and doing a little unit conversion. I wrote the equation I was going to use in variable form. I plugged in the numbers for it and solved it. And that's about all you're going to need on the solutions. Have enough steps so that a reader can follow it. You can assume your reader is half decent at algebra so they could go from this almost immediately to this. If you want to write in the step, that's fine, the extra steps. But you don't need to explain them or anything like that. So there's A, and that's all you had to do for it. For part B, you've got a choice about how to do it. You want to know through how many radians does the wheel turn while stopping? Well, one way of doing that would be to do theta is going to equal theta naught plus omega naught t plus 1/2 alpha t squared. And what you want is theta minus theta naught. So delta theta is going to be theta minus theta naught. That's going to equal omega naught t plus 1/2 alpha t squared. And the t that matters here is this one you just figured out. You could also do this. You could say that omega squared is going to equal omega naught squared plus 2 alpha delta theta. This is the rotational analogy of v squared equals v naught squared plus 2a, plus 2a delta x. So that equation works just fine too. And at the end, omega squared is going to be 0. So you can say that equals 0. Delta theta will equal minus omega naught squared divided by 2 alpha. And so we have that there. And now you could just plug in the numbers. Minus 10.5 radians per second. Oh, by the way, I'm doing something that I don't want you to do, where I was working in columns here, but just have your solutions go linearly downward. Don't go popping over into columns, but I didn't use this anyway. So anyway, that thing squared, not very easy to see. And then 2 times minus 2.00 radians per second squared down there. And so then you'd just have delta theta equals whatever amount it is. Now, if you were doing this for yourself, I would hope you would write a reflection paragraph after that. I haven't decided yet whether or not I'll have you write reflection paragraphs on each one of these things, but it's a useful exercise. And once you've done the problem, it shouldn't take long, maybe 3 minutes or less to write a reflection paragraph, maybe 1, I'm not sure. But I would encourage you to always write a reflection paragraph, I guess. It's just a way of thinking about the process that you just went through, and it'll help to cement it in your mind. I realized the necessity of this a few years ago, and I may have mentioned this fall quarter, but I had a student, I was doing an office hour down in the STEM center, and I think it may have had to do with rotational stuff, but he'd come over and ask me how to solve a problem, and it turned out to be a conservation of energy problem. Might have been an electricity problem. And so I showed him how you could have the initial energy and the final energy, and you could look at the change in electric potential energy or something like that. And so he went back and solved the problem. And about 5 minutes later, he came and asked me another question that would have used exactly the same technique. Whereas I think if he'd had to write a reflection paragraph on the problem he'd just solved, it should have immediately occurred to him how to do that next problem. But those are things that happen. So that's the reason for the reflection paragraph. We learn by repetition, and it helps to keep thinking about things. Okay, here's another problem. I'm not going to bother with the given and to be determined on this one, but we have a grinding wheel. Initially at rest is rotated for 8 seconds with a constant angular acceleration, 5 radians per second squared. The wheel is then brought to rest with uniform negative acceleration in 10.0 revolutions. Oh man, we've got things mixed again, but that's okay. Determine the negative acceleration required and the time needed to bring the wheel to rest. So it's similar to the last problem, except that we don't know the initial angular velocity when it's beginning to be brought to rest, but we can figure it out. We know that it's rotated for 8 seconds with a constant angular acceleration. In fact, we can figure that out. Omega, and this will be after 8 seconds of startup, omega will equal omega naught, which is 0 in this case, plus alpha t. Well, alpha they give to us 5.00 radians per second squared. 8 seconds is how long this goes on for. I can do that in my head. And we get 40.0 radians per second. Notice I didn't just write 40 radians per second. The only way I can show that it's 3 significant figures, well, not the only way, but a way I can show 3 sig figs is 40.0. That 0 after the decimal place is significant. I could also write it in scientific notation, which is kind of unnecessary here, but 4.00 times 10 to the first radians per second. So that's what I have. Then it's brought to rest in 10 revolutions. Well, here's something that'll work. Then, while stopping, alpha is going to equal, it'll be negative, but I don't know what it is. And I can say that V, whoops, not V, I was back in my linear motion. I can say that omega equals omega naught plus alpha t, and that's going to equal 0 when it's brought to rest. Let's see, and it's brought to rest in 10 revolutions. That's kind of inconvenient. But I could say something like theta is going to equal theta naught plus omega naught t plus 1/2 alpha t squared. And I know omega naught, but I don't know alpha, and I don't know t. But there's that third equation, which is omega squared equals omega naught squared plus 2 alpha delta theta. And this one doesn't involve t. I'll find t eventually, but I know what this is because it's going to be 0 when it's brought to rest. I know omega naught, that's what I just figured out. I like it that way better. So I'll call that, well, that's not omega naught. It will be for this part. Yeah, while stopping, alpha is negative and omega naught is 40.0 radians per second. I could do that. Okay, but anyway, this will be 0. This is my 40 radians per second. The delta theta is 10 revolutions, but those aren't convenient units, but I can figure it out from those. Delta theta is 10.0 revolutions. This looks like a problem I rewrote to give it 3 significant figures, because I'd be willing to bet that the book I took it out of just said 8 seconds, 5 radians per second squared, and 10 revolutions. And you were supposed to assume 3 sig figs. Anyway, 10 revolutions, and I just multiply by 2 pi radians for every revolution. Okay, and hopefully you're familiar enough with radians and revolutions to know that right off the top of your head. Okay, well, that looks like 20 pi radians, which I think is 62.8 radians is the angle that it would turn through. Check that to be sure, but I'm pretty sure that's right. Anyway, so there's delta theta. What don't I know? I don't know alpha. Well, let's figure it out. Omega squared at the end is going to be 0, is going to equal my 40.0 radians per second squared plus 2 times alpha times 62.8 radians. And let's see what we get here. Solving for alpha, and you can just go ahead and do this in one line. It'll be, let's see, negative, I'd kick alpha across, divide by everything else, minus 40.0 radians per second squared divided by 2 times 62.8 radians. Unit-wise, I'll have radians squared per second squared on top. I'm dividing by radians, so I'll get radians per second squared, and it'll be minus something or other. 1600 divided by, oh, I've got another 2 down there. 2 times 62.8. If I didn't make a mistake while I was talking and writing, it should be minus 12.7 radians per second squared. So this procedure may seem somewhat familiar when you relate it back to the constant acceleration motion that we studied fall quarter. So I know I've got this batch of equations that I can use, and that's what I'm doing. Oh, it also wants to know the time needed to bring the wheel to rest. Well, I know alpha now, and so this equation up here that when I was fishing for a way to solve this, I wrote it down. I can just say that omega is going to equal omega naught plus alpha t equals 0, or the t is going to equal minus omega naught over alpha, which is minus omega naught was 40 radians per second divided by minus 12.7 radians per second squared. See how when I keep track of the signs carefully, I'll end up with a positive time, which I'd expect to have. And amazing, I get 3.14 seconds. And probably if I solve this thing carefully with variables all the way through, I'd know that that ends up being pi seconds, but I'm not positive about that. Okay, so there's another one where I just used those equations that we developed yesterday. Let's see. Here's something about cars and rolling things, and maybe I'll do something on the back of one of these previous sheets here, and we'll imagine a horizontal surface. I don't know where that nice green thing I used yesterday went. This ought to work. Okay, so here's the center of the wheel. The wheel is rolling along here like this, and we'll plug in the numbers on this a little bit later, but something interesting is that the center of the wheel is going to have a velocity in this direction, and as the wheel rolls through a bunch of rotations here without slipping, the distance it travels is going to be the circumference of the wheel, which is 2 pi r times the number of rotations that it does. When you divide that by the time it takes, you find out that the velocity of the center of wheel, the velocity of the center of the wheel is actually equal to the radius of the wheel times omega. Well, that's also the speed of a point on the rim of the wheel with respect to the center of the wheel. It's a relative velocity thing that's kind of complicated because it's constantly changing orientation. When we had relative velocity problems, last quarter, we had a fixed velocity with respect to something. And in this case, you have one that's constantly changing. But anyway, the speed of a point on the rim of this thing is also equal to r omega, but it's the speed with respect to the center. The velocity with respect to the Earth, you'd have to add the velocity of the center of the wheel to that velocity, which is constantly changing direction as it's moving along there. So it's a little more complicated, but that's something that comes out of something like this. So if I go, and this is the velocity of the center of the wheel. So if I come back to this thing, an automobile accelerates from 0 to 30.7 meters per second. That's nice. In 6.03 seconds, they have diameters of 0.422 meters. What's the angular acceleration of each wheel? Well, let's see. If it's got a diameter of 0.422 meters, it's going to have a radius that's half of that. So the radius is 0.211 meters. Let's see. I can't remember. We have a person who used to teach math here, and for years he taught calculus and linear algebra and some of that stuff. But I think one day I went out with a meter stick and measured the height of one of the wheels on his car. And that may be where I got this number from. I'm not sure. Anyway, that's the radius of this thing. Now, the omega for this thing, or the speed of the car is going to equal that radius times omega. And I'm using a capital R for radius this time. That doesn't matter. And so I can figure out what omega is. It's just going to equal that V divided by the radius, or 30.7 meters per second divided by 0.211 meters. Now, when you look at this, meters per second divided by meters, the meters will divide out and I'll end up with per seconds, which is the actual physical unit of omega. But it's usually written as radians per second because just so that we know it's a rotation, it's just a way of keeping track. A radian is a meter divided by meter. It's a dimensionless quantity. And so I'll write radians over here when I get this. So 30.7 divided by 0.211. I get 14.6 radians per second. Okay, well, it went from 0 to 30.7 meters per second in those 6.30 or 03 seconds. It also went from an angular velocity of 0 to 14.6 radians per second in those same 6.03 seconds. So it started from rest, it wasn't rotating, it wasn't moving, and it did that. So the angular acceleration is just going to be delta omega over delta t, or in this case, omega minus 0 divided by delta t. So I'll just plug in the numbers here. 14.6 radians per second divided by 6.03 seconds. And I'll get some nice number for this. Of 2.42, or no, 24.2. Wait. Oh, this should have been, nobody caught that, 146 radians per second, because I wasn't even looking at my calculator. Anyway, 146 radians per second. And so this would end up being, that's supposed to be over there, 24.2 radians per second squared. Now, sometimes you may see terms regarding this. You might see this thing written as 146 seconds to the -1. And you might see this thing written as 24.2 seconds to the -2. Because the actual physical units in here are just seconds to the -2. The radian, again, it's a ratio of identical units and is dimensionless. But we'll keep it there just so we know that we're talking about rotations and angular velocity and stuff like that. Okay, I think I wanted to do a problem or two that had rotational inertia in it, something we looked at yesterday. And there is a section in this chapter, I think it's section 9.6, on calculating rotational inertia. And it for that, you would be using the expression that the rotational inertia of some object ends up equaling r squared dm. And if you've got some weird shaped object here and you're calculating the rotational inertia about this point, you'd imagine some little spot out here, which you call dm, and then r is the distance from your axis of rotation out to that thing. So the r that's in here is a variable. dm is usually some kind of an expression that's kind of complicated to figure out. And but that's how you would calculate this. And you would do this operation of integration, which is not very well written, but that's my version today of the integration symbol. You can make it look a little nicer than that. Put limits on it, but the limit in this case would just be integrating, adding up all the contributions from all the different parts of this weirdly shaped object. Now, in our book, we don't do any weirdly shaped objects, so that's kind of nice. But there is a section in the chapter on that, but we're going to skip it because those of you in second quarter calculus haven't seen integration yet. Maybe you have. It's already the second day of winter quarter, and that's the quarter you typically do integration in, but I doubt it. Anyway, we're just not going to do that. However, in your textbook for Planck is a table that shows the moments of inertia of various bodies. And this has all of the ones that we would typically ever do. And so we've got stuff like a slender rod with the axis through the center, a slender rod with the axis through one end, a plate with the axis through the center, a plate with the axis along one edge. And if you ever take statics and dynamics, the engineering classes, you will do the integrations for these things, except, well, these are the easy ones. You'll get some irregular objects that you'll be doing them for. And it turns out that the mathematical expression for determining things like the strength of a beam relative for a load that's put on it, when how much it'll bend or something like that, depends on a calculation that's identical to calculating its rotational inertia. And so that's why you do that in engineering. But it doesn't have anything to do with rotation in that case. It just has something to do with its strength. But we'll look at things like cylinders and thin-walled cylinders, which is basically a hoop, and spheres and thin-walled hollow spheres, stuff like that. But when we get to the next chapter with a little bit of rolling motion, but we're not going to need anything more than what's in this table. And I provide you with this when we have the test anyway, so it's not something you'll have to worry about. The moment of inertia calculations, these are, you might find this helpful when you get to calculations like this in your calculus class. So you might remember that that happens to be here. Okay, So we're not going to have to worry about those things too much. We'll just use the results of them. So measure the amount of energy used by an electric motor to speed up a wheel from rest. This is a little weird. I think I didn't copy this problem quite right. Show that to bring the wheel from rest to an angular speed of 3.7 radians per second. The motor exerts 7,600 joules. I wonder what in the world I did with this problem. I don't have this textbook with me at home. Oh, measurements of the amount of energy used by an electric motor. Okay, that makes more sense. So the motor and the wheel have practically negligible amounts of friction or other type of damping. So in getting the thing from 0 to 3.7 radians per second, it expended 7,600 joules. That would be the kinetic energy that the motor gave to the wheel. And so we could say that the kinetic energy is going to equal 1/2 I omega squared. And that was equal to 7,600 joules when omega is equal to 3.7 radians per second. Okay. Well, we could use this to figure out the rotational inertia of this wheel. So let's do that. That means I is equal to, well, let's see, just solving for that, it would be 2 times 7,600 joules divided by 3.7 radians per second squared. Now here we've got radians down there, but we really just want to think of those things as per second squared. And so we'll have that. But then we want to remember, what in the world is a joule? Oh, well, that's our unit of kinetic energy. Remember, kinetic energy was 1/2 mv squared. Okay, it's also going to be I omega squared, but that's going to be kilograms meters squared per second squared is what a joule is. So in my head, I'm going to do 2 times 7,600, 15,200 kilogram meters squared per second squared divided by 3.7 radians per second squared. And again, the radian is just a placeholder unit. I've got per second squared on top, and I'll have per second squared on the bottom. And the radian, I'll just let it disappear because it's just a placeholder. And I'll end up with kilogram meter squared for the units of rotational inertia, which makes sense. I'm going to go ahead and write the number down first. And I only have 2 sig figs, so. And I get about 1,100, or 1.1 times 10 to the third kilogram meters squared. Okay, those units make sense because yesterday when I did that sort of crude calculation of what the rotational inertia would be, I came up with the thing that said it would be the sum of m sub I r sub I squared for all the different pieces of some rotating object. Well, this is going to be kilograms. This is going to be meters squared. So that's why rotational inertias have those particular units. And so let's see. Okay, now it turns out I didn't actually need to calculate this for this problem, and I'll show you why. I'll call this omega 1 up here. And then I'm told that in a second use of the motor and the wheel motor expends 9,600 joules to bring the wheel up from rest to an unmeasured angular speed. What is the unmeasured angular speed? Well, I can say that 1/2 I omega 2 squared is equal to 9,600 joules. Now, I figured out omega, and so I could just plug that in here and solve for that. But I can also use my initial problem, 1/2 I omega 1 squared is equal to 7,600 joules. And if I divide this equation by that equation, I'll end up with omega 2 squared over omega 1 squared is equal to, actually the joules will divide out, the hundreds will divide out, and I'll have 96 over 76 left. And so you can just solve for omega 2 that way. So omega 2 will equal omega 1 times the square root of 96 over 76, which is, so I'd have 3.7 times that square root and I get about 4.2 radians per second. So I did this just as an exercise to show how you could figure out the rotational inertia of something and its units as well. But we could have then used that here, but we didn't have to. I would have preferred to do it this way. The math is just easier and fewer steps. Okay, let's see if we can get another one done here. I'm going to skip this one. What is the rotational inertia of a uniform 4-kilogram iron rod, 0.25 meters long, about an axis through its center point and perpendicular to the rod? Okay, well, I is going to equal, I don't expect you to memorize this. Slender rod, axis through center. The moment of inertia is 1/12 ml squared. Okay. So that's all it is. So we just have to plug in the numbers here. 1/12. The mass is 4.0 kilograms. And the length is 0.25 meters. And we square that. So that's all there is to it. It's just plug and chug on a formula. You probably did geometry formulas like this in maybe 7th grade, something like that. So 4 times 0.25 squared divided by 12. Okay, then I get 2.08. How many significant figures? Only 2. So 2.1 times 10 to the minus 2 kilogram meters squared. Okay, well, that was easy. That was part A. Part B is about an axis through an end point and perpendicular to the rod. Oh, well, I have to open the book again. It's already open. In that case, slender rod, axis through one end. The blue thing on here is the axis. Oh, it's 1/3 ml squared. Okay, so in that case, I is equal to 1/3 ml squared, which is just going to be 1/3 times 4.0 kilograms times 0.25 meters squared. And I guess I could figure this out. Okay, for that one, I get 8.3 times 10 to the minus 2 kilogram meter squared. Why would I get different things? here's what happens. If we imagine this is our iron rod, oops, some of those should be dashed lines. In the one case, the first case, we've got an axis that goes right through the center of it. And for every little chunk of material on here, okay, if that's an M sub I, something like that, this would be its R sub I. And this distance here is 1/2 L from the center of the axis out to the end of it. And I would add up a whole bunch of things, my M sub I and my R sub I squared. And I'd add those up over this whole half of the rod, and then I'd just double it to figure out the thing for the whole rod, because when you square these lengths, they all come out positive anyway. So that's how I would do it. But in the other case, I'd have my rod here, and half of the calculation or part of the calculation would be absolutely identical to what I did here. I'd have a little M sub I, and this distance here is 1/2 L. And so I'd do a sum like this, and for this half of the rod, it would be exactly what I got for this part. Exact same calculation. But then the other part of the rod, I'm starting out already 1/2 L away, and I go out here farther, and that distance gets squared. And so it makes it have a larger moment or rotational inertia calculated about an axis when it's attached to the end. And it's because of that extra weight that's farther away from the thing. And so that's why it matters. Now, turns out the lowest rotational inertia for an object is always going to be the one that goes through the center of mass of the object. And so that's the least amount. The rest of them are all bigger. They do a proof in the book of something called the parallel axis theorem. But let's imagine that we have some weird object sitting here like this, and over here is where the center of mass of the thing is. And then maybe we've got an axis that goes through this point P instead. And we want to know what's the rotational inertia of this thing about this point P. Well, the way you do it in calculus is that you would I sub P, you'd end up going through some big summation, and you'd have M sub I, R sub I squared. But it turns out that the result you get, in this case, we use something called the parallel axis theorem. It ends up equaling the moment of inertia through the center of mass, so the moment of inertia like that, plus the total mass of the thing times the distance between point P and the center of mass. And it's a really pretty simple proof to show that this is the case. They do it in about 2 paragraphs in the textbook. And so you might check this out. It's called the parallel axis theorem. Well, let's see how that works for the that slender rod that we had here. For the slender rod, we had that the moment of inertia through the center of mass was 1/12 ml squared. Okay, and this is the rod where it's got a length L and a mass M. Okay. Well, let's do one about the end using the parallel axis theorem. Okay, and I'll just call this, I don't know, through the end. I is going to equal ICM, the moment of inertia through the center of mass, plus the total mass of the thing, times this distance here, which is 1/2 L squared. Okay, so what do we get? We'll get 1/12 ml squared plus, oh, when I square this, I'll get 1/4 ml squared. And let's see, 1/4 I think is 3/12. So I'll have 3/12 and 1/12 is 4/12 ml squared, which is 1/3 ml squared. Okay, I think I'd look that up, and that is what it is. So these things aren't quite as mysterious as you may think. They all come out of relatively simple calculations, but you do need that tool of integration to be able to do these things. They get a little more complicated when you're dealing with something like a rectangle or a sphere, but for things like cylinders through an axis going right down the axis of the cylinder, it's not too bad. And so we'll do some more things with that. In fact, tomorrow we're starting chapter 10. Let's see, with what we've done so far, you should be able to do about the first 4 problems on the homework assignment, I think. You are going to have to, I think I give you the density of iron. One of the problems you need the density of iron for. You also need to know that density is mass per unit volume, but go ahead and dive into that. Let's see, the lab for this week is radioactive decay, and I'd like to put it off to tomorrow. I have to repair something on my computer here this afternoon, and I may not get that done in time to be able to meet with you for the lab. But for the lab, we're going to use that Excel file with the radioactive decay data, except this time, instead of just graphing a couple of curves, we're going to figure out the half-life of the different isotopes. And you'll just pick one isotope and we'll go through that. But got a couple handouts that I'll give you on that. And I'm going to be adding more and more stuff onto the Canvas page here coming up. But for today, that's kind of it. So I'm going to stop the share. Does anybody have any questions that popped up during this stuff? Okay, well, I'll see you again tomorrow morning. We're starting chapter 10. So sometime later today, I should have posted which sections in chapter 10 we're going to be doing here. But go ahead and take a look at the first 2 or 3 sections in chapter 10 for tomorrow. And I'll see you then.